A ring of fire orbits the ultimate abyss. This is not special effects, but reality at the edge of a black hole, where gravity twists the rules of physics into a spectacle of pure cosmic power. That brilliant, swirling structure is an accretion disk, the universe's most powerful engine. It is not built from steel, but forged from superheated gas and the very fabric of space-time. This journey explores those fiery rings, the chaotic and beautiful disks that feed black holes. Understanding them unlocks profound secrets, from how galaxies are born to where we might one day find energy sources beyond our wildest dreams. By the end, you will see how these luminous maelstroms hold the key to the cosmos' greatest puzzles. We will uncover what happens to matter in its final, violent moments and ask if the physics of these disks could ever be harnessed. What does such unimaginable power make you wonder about our place in the universe? Think of the universe as a grand, chaotic restaurant and a black hole as its most insatiable customer. The meal it is served arrives on a very specific kind of plate, a structure so vast and violent it defies simple description. This is the accretion disk, a flattened, spinning whirlpool of superheated material orbiting the point of no return. At its heart, the concept is almost elegantly simple. Any massive object with a strong gravitational pull can gather a crowd of cosmic debris around it. Gas, dust, and the shredded remains of unfortunate stars are pulled inward, but they rarely fall straight down. Instead, they possess a tiny amount of sideways motion, a leftover spin from their previous journey through the galaxy. This spin, combined with the relentless inward pull, forces the material into a flattened, rotating disk, much like how a ball of pizza dough spreads out into a flat circle when a chef spins it. This process is universal. You will find these disks feeding newborn stars as they gather material from a surrounding cloud, and you will see them around the dense corpses of dead stars like white dwarfs and neutron stars. But when the central body is a black hole, the dinner service becomes a spectacle of pure, unbridled physics. The gravity is so intense, the speed so fantastic, that the simple act of matter spiraling inward unleashes energies that outshine entire galaxies. The water swirling down a drain is a peaceful analogy for this cosmic process, but here the water is a plasma hotter than the core of a star, and the drain is a bottomless pit where the laws of physics as we know them cease to exist. This is where our story truly begins, at the edge of that ultimate drain, watching the universe serve a meal of pure light and fury. That brilliant ring of fire does not appear from nothing. It requires fuel, a constant cosmic delivery of matter to keep its inferno burning. So where does all this material come from? The answer depends entirely on the type of black hole you are observing, and it reveals a universe of violent relationships. For the smaller, stellar mass black holes, the story often begins with a partner. Many of these black holes exist in binary systems, locked in a gravitational dance with a living star. Over time, the black hole's immense gravity can siphon material directly from its companion. This theft happens in two main ways. Stellar winds, like a constant, powerful breeze blowing from the star's surface, can carry particles across the gap where they are captured by the black hole's pull. In more extreme cases, the black hole can actually distort the star itself, pulling matter from its outer layers in a continuous stream. This process, called Rochlube overflow, is like a cosmic water balloon being stretched until it spills its contents directly toward the waiting abyss. Each stolen atom joins the swirling procession of the accretion disk, feeding the glow we can see from across the galaxy. But for the supermassive giants that lurk at the hearts of galaxies, the menu is far more extravagant. Their immense gravity influences everything around them. Sometimes an unlucky star wanders too close. In a cataclysmic event called a tidal disruption, the black hole's tidal forces stretch and shred the star into a long, thin stream of gas, a stellar spaghetti that then spirals in to form a temporary, brilliant accretion disk. Other times, vast clouds of interstellar gas drifting for eons are funneled toward the galactic center, providing a more steady, if chaotic, supply of fuel. And during the colossal mergers of entire galaxies, the resulting chaos drives unimaginable amounts of gas and stars directly toward the central black holes, triggering outbursts of light that can be seen across the universe. This is the crucial dynamic relationship. A black hole alone without this incoming material is truly dark and invisible, a silent phantom in the void. It is the accretion disk born from this stolen or disrupted matter that transforms the black hole into a beacon. The fiery ring is not just a feature, it is a story, a luminous record of the black hole's violent interactions with its cosmic neighborhood. Without that ongoing conversation of gravity and matter, the greatest shows in the universe would play out in perfect, absolute darkness. The stolen matter now faces a dramatic choice dictated by a single, stubborn property. It possesses angular momentum, a cosmic version of the spin you give a basketball on your finger. This spin prevents it from falling directly into the black hole. Instead, it is forced into a wide, looping path like a satellite in a degrading orbit. Countless particles, all with slightly different speeds and trajectories, begin to crowd together, colliding and merging their paths. This chaotic traffic jam gradually settles into a single, unified direction of rotation, flattening into that familiar disk shape under the influence of gravity. But this is where the true transformation begins. This disk is not a serene, orderly carousel. It is a turbulent sea of superheated gas where particles are packed incredibly close, moving at ferocious speeds. As these layers of gas scrape past one another, an immense internal friction arises, a property physicists call viscosity. Think of stirring a thick pot of honey with a spoon, feeling the drag and resistance. Within the accretion disk, this viscous drag is catastrophic. It robs the material of its precious orbital energy, converting that lost motion into an astonishing amount of heat. The friction is so intense that the gas is heated to temperatures of millions of degrees, causing it to glow not just with visible light but with X-rays and gamma rays. With each microscopic collision, each act of viscous braking, a particle loses a tiny bit of its sideways velocity. This allows gravity to win a little more, tugging the particle onto a slightly tighter, faster orbit. The result is a slow, inevitable spiral inward, a death march of countless particles shedding their energy as blinding light as they creep toward the edge. This spiral continues until the particles reach a final boundary, a point of no return known as the innermost stable circular orbit. Within this critical radius, the pull of gravity becomes so overwhelmingly strong that stable orbits are impossible. There is no more slowing down, no more spiraling. Any material that crosses this invisible line is not orbiting anymore, it is simply falling, accelerating into the oblivion of the event horizon. The brilliant glow of the accretion disk is literally the last scream of light from matter being stripped of everything it has, its final energy payment before it vanishes forever from our observable universe. This transformation of motion into light creates temperatures that are almost impossible to comprehend. Within the inner regions of an accretion disk around a stellar mass black hole, the gas is routinely heated to around 10 million Kelvin. To put that into perspective, the core of our Sun burns at a mere 15 million Kelvin. We are talking about a ring of matter, not a star, that achieves a comparable stellar inferno purely through friction and gravity. At these temperatures, atoms are utterly destroyed. Electrons are ripped from their nuclei, creating a seething, fourth state of matter known as plasma. This superheated plasma does not glow with the familiar yellow-white light of a candle or even our Sun. It radiates its tremendous energy in the form of X-rays, a high-frequency light invisible to our eyes but detectable by telescopes in space. This is the primary signature that allows astronomers to find these hidden cosmic engines. The temperature, however, is not uniform and depends dramatically on the size of the black hole itself. Around a supermassive black hole, the accretion disk is vastly larger and more diffuse, while still unimaginably hot by any earthly standard. With temperatures in the hundreds of thousands of Kelvin, it is comparatively cooler. This massive disk glows fiercely in ultraviolet and optical light, bathing the central regions of galaxies in a brilliant, haunting radiance. This difference in temperature directly dictates the color of the cosmic fire. A smaller, tighter disk around a stellar corpse screams in X-rays, while the vast feeder disk of a galactic giant shines with the integrated light of a billion stars. Regardless of the central monster's size, the process floods the universe with radiation across the entire electromagnetic spectrum. From the long, slow waves of radio energy emitted by the outer, cooler disk material, to the blistering, short wavelength gamma rays produced in the most violent magnetic eruptions near the event horizon, an active accretion disk is a full-spectrum lighthouse. This is why quasars, the incredibly luminous cores of distant galaxies powered by supermassive black holes, can outshine every star in their home galaxy combined and be seen across billions of light years. The fiery ring is not just hot, it is the universe's most efficient and powerful converter of mass into pure energy, a beacon that turns the act of consumption into the brightest light we can see. That brilliant, multicolored light is more than just a beacon, it is a detailed message. To an astronomer, the glow from an accretion disk is not a simple white noise of energy. It is a complex fingerprint, a barcode of information written in the language of physics. They read this message using a technique called spectroscopy, which acts like a cosmic prism, splitting the light into its individual wavelengths to reveal a detailed spectrum. Within that spectrum are dark and bright lines, the unique signatures of specific chemical elements like hydrogen or iron, absorbed or emitted by the swirling gas. In a calm, stationary laboratory, these lines are sharp and precise, but around a black hole they are stretched, blurred, and twisted into bizarre shapes, telling a story of extreme environments. The first clue comes from temperature. The scorching inner regions of the disk, heated to millions of degrees, emit most of their energy as short wavelength X-rays. The cooler outer zones glow with longer ultraviolet or visible light. By analyzing the mix of wavelengths, scientists can essentially take the disk's temperature from millions of miles away, mapping its hot inner rim and cooler outer edges. But the truly fascinating distortions come from motion and gravity. As the disk spins, the gas on the side spinning toward us has its light waves compressed, shifting them toward the blue end of the spectrum. The gas spinning away has its light stretched, shifting toward red. This is the Doppler effect, the same phenomenon that changes the pitch of a passing siren. In the furious whirl of an accretion disk, this effect smears those sharp spectral lines into broad, fuzzy bands. The amount of broadening tells astronomers exactly how fast the disk is spinning, a key to understanding the black hole's ferocious grip. The most profound distortions, however, are born from Einstein's theory of relativity. The intense gravity near the event horizon acts like a lens, bending the very paths of the light rays escaping the disk. It also causes gravitational redshift, stretching the light to longer, redder wavelengths as it struggles to climb out of the gravity well. This warps the spectral lines in a unique, predictable way. A particular spectral line from iron, called the iron K-alpha line, has become a crucial tool. It is a bright, recognizable feature that gets stretched and skewed by these relativistic effects. By studying the exact shape of this distorted iron line, scientists can perform a kind of remote sensing tomography, mapping the structure and velocity of the innermost disk regions, right down to the precipice of the event horizon itself. It is as if the black hole's gravity is signing its own name on the light, and we are finally learning how to read the signature. The light we decode from these disks is a theoretical triumph, but for decades the central engine itself remained a silhouette against the glow. All that changed on April 10, 2019, when a team of scientists unveiled an image that made history. It was not a crisp photograph, but a painstakingly constructed radio image of the supermassive black hole at the heart of the galaxy Messier 87. This was the work of the Event Horizon Telescope, a project of breathtaking ambition. It was not a single telescope, but a planet-sized virtual instrument created by linking 8 radio observatories across the globe, from the high deserts of Chile to the volcanoes of Hawaii and the frozen plains of the South Pole. By synchronizing their observations with atomic clocks, these separate dishes acted as one giant eye, achieving a resolution sharp enough to read a newspaper in New York from a sidewalk cafe in Paris. Their target was the shadow of the black hole, a dark central region silhouetted against the brilliant light of its own accretion disk. And there it was, a glowing, fuzzy ring of orange and yellow, a cosmic donut of fire with a dark heart. That iconic ring of fire was the direct image of the black hole's shadow, warped and magnified by its own immense gravity. The light forming the ring comes from the innermost part of the accretion disk, its photons bent on impossible paths around the event horizon before some of them finally escape toward us. The image was not symmetrical, however. One side of the ring was noticeably brighter. This was not a flaw, but a spectacular confirmation of decades of theory. That asymmetry is the smoking gun of a rapidly spinning disk. The brighter side is where the hot plasma is whirling toward us at a significant fraction of light speed, its radiation intensified by a relativistic effect called Doppler beaming. The dimmer side is where the material is rushing away, its light stretched and dimmed. The dark central shadow, about 2.5 times larger than the event horizon itself, is the signature of spacetime itself being twisted into a bottomless pit. That single, grainy image connected a century of abstract mathematics to tangible reality. It proved that the monstrous gravitational engines we calculated actually exist in the shapes we predicted, complete with their swirling, superheated feasts of light. We were no longer just listening to the echoes of the cosmos, we were staring directly into its fiery, beating heart. That iconic image of a fiery ring, however, only tells half the story of a black hole's influence. From the poles of this monstrous engine, something even more spectacular erupts. Twin beams of energy, sharper than any laser and stretching across cosmic distances, blast out at nearly the speed of light. These are relativistic jets, the black hole's unimaginably powerful exhaust system. They do not consist of the material falling into the abyss. That fate is sealed. Instead, they are born from a fraction of the titanic energy generated by the accretion disk itself, a portion of the inferno that is redirected and launched back into the universe. The mechanism is a masterpiece of magnetic physics. The swirling, superheated plasma of the disk is threaded with magnetic field lines. As the disk rotates at fantastic speeds, it drags these magnetic fields along, twisting them into incredibly tight, powerful coils, like cosmic rubber bands wound to their breaking point. Near the black hole's poles, where the inward pull of gravity and the outward pressure of radiation find a precarious balance, these wound-up magnetic fields find an escape route. They act as a slingshot, channeling and accelerating some of the charged plasma from the inner disk into two oppositely directed, incredibly focused beams. These jets are not diffuse sprays, they are collimated, meaning they stay tightly focused over distances that dwarf entire galaxies, a feat of natural engineering that our most powerful particle accelerators cannot replicate. The impact of these jets is nothing short of galactic-scale engineering. They can punch through the surrounding gas of their host galaxy and travel for millions of light years into the intergalactic void, often becoming the largest single structures in the universe. Where these beams of raw energy slam into clouds of interstellar gas, they can trigger shock waves that both compress material to birth new stars and blow other gas away, halting star formation entirely. In this way, a black hole's jets act as a cosmic regulator, capable of giving life or imposing a stern quarantine on entire galactic neighborhoods. For the most luminous objects we see in the distant cosmos, these jets are the primary power source. When a jet is pointed almost directly at Earth, we see an object called a blazar, a source of such violent and variable radiation it floods our telescopes with gamma rays and other high-energy light. The more common quasar gets its brilliant glow from the intense heat of the accretion disk, but its jets shape its environment for eons. This transforms our view of the black hole from a mere consumer of matter into a dynamic cosmic powerhouse. It is not just a drain in the fabric of space-time, it is an engine that takes gravitational energy, converts it into light and motion, and then projects its influence across the cosmos with these brilliant, precise beams. The fiery ring feeds the beast, but the jets announce its power to the universe. The brilliant jets and intense radiation from these central engines do more than just light up the cosmos, they shape its very architecture on the grandest scales. This is most evident when we turn our gaze to the supermassive black holes that reside at the heart of nearly every large galaxy, including our own Milky Way. Our galactic center is home to a relatively quiet giant named Sagittarius, a star, a behemoth with a mass 4 million times that of our Sun. For most of its recent life, it has been dormant, its accretion disk faint and its appetite modest. But this quiet coexistence hints at a deeper, more profound connection. Astronomers now see compelling evidence for a grand cosmic symbiosis, a theory called the co-evolution hypothesis. This idea suggests that the growth of a supermassive black hole and the growth of its host galaxy are not separate events, but are intrinsically linked, each influencing the other across billions of years. Think of a galaxy and its central black hole as partners in a vast, slow dance. As the galaxy gathers gas to form new stars, some of that gas inevitably funnels toward the center, feeding the black hole and igniting its accretion disk into an active, luminous state. This is the black hole's growth phase, but the black hole does not just consume passively. In return, the tremendous energy released by its accretion disk and the powerful jets it launches act as a form of cosmic feedback. These energetic outflows blast through the surrounding galactic gas like a hurricane. This process has two major effects. First, it can heat vast reservoirs of cool gas, preventing that gas from collapsing under its own gravity to form new stars. Second, in more violent episodes, it can physically push that gas right out of the galaxy's central regions entirely, stripping away the very fuel for future stellar generations. In this way, an active black hole acts as a natural thermostat or a regulator for its own galaxy. It can quench star formation, effectively putting a limit on how large the galaxy can grow. This feedback loop creates a remarkable balance. Observations show a surprising correlation between the mass of a galaxy's central bulge of stars and the mass of its supermassive black hole. Larger galaxies with more stars in their central hubs consistently host proportionally larger black holes. This tight relationship suggests their growth histories are intertwined. A galaxy provides the food, and the black hole, once fed, returns the favor by controlling the kitchen, deciding when and where new stars can be cooked up. This positions the humble accretion disk as far more than a local spectacle. It is the control panel for a galaxy-scale engine, a key player in determining whether a galaxy becomes a bustling metropolis of stars or a quiet, aging suburb. The fiery rings feeding these monsters are not just destructive ends, they are creative forces sculpting the cosmic landscape and tying the fate of a black hole to the destiny of the entire galaxy it calls home. While the grand dance of galaxy and black hole unfolds over eons, the menu can include a sudden, spectacular special. This is a tidal disruption event, the moment a star's ordinary life ends in an extraordinary flash. It begins with a simple cosmic misstep. A star, perhaps one much like our own Sun, wanders on an unlucky orbit that brings it perilously close to a supermassive black hole. As it crosses a critical threshold, something profound happens. The force of gravity on the side of the star facing the black hole becomes overwhelmingly stronger than the force on the far side. This difference, the tidal force, stretches the star lengthwise while simultaneously compressing it from the sides. In a matter of hours, the star is pulled apart into a long, thin stream of superheated gas, a process physicists grimly and accurately call spaghettification. The star's own gravity, which once held it together in a perfect sphere, is utterly defeated by the black hole's immense pull. This stream of stellar debris does not vanish immediately. About half of the shredded material is flung out into the darkness on hyperbolic orbits, lost forever. The other half, however, finds itself on elongated paths that loop back around the black hole. This returning material, rich with the hydrogen and helium that once fueled the star's nuclear furnace, begins to collide with itself. Different parts of the stream, traveling at different speeds, pile up and intersect. This chaotic traffic collision dissipates energy, allowing the gas to settle into a temporary, intensely hot accretion disk around the black hole. For a brief cosmic moment, a new and brilliant ring of fire is born from the remains of a star. To an astronomer's telescope, this cataclysm announces itself as a sudden, violent flare of light. In a galaxy that may have been quiet and dark at its core for millions of years, a new point of brilliance erupts. It shines across the entire electromagnetic spectrum, from X-rays generated in the searing inner disk to visible light and infrared radiation from the outer, cooling debris. This flare does not blink out quickly. It can brighten over weeks or months as the disk forms and reaches peak intensity, then slowly fade over months or years as the black hole consumes the stellar meal. The light curve, the graph of its brightness over time, becomes a unique fingerprint. By analyzing how the light rises and falls, scientists can deduce the mass of the black hole, the type of star that was destroyed, and the physics of how the accretion disk formed and evolved. These events are cosmically rare, occurring perhaps once every 10,000 to 100,000 years in a typical galaxy. Catching one is a triumph of modern sky surveys that constantly scan the heavens for transient flashes. But when we do catch one, it provides an unparalleled laboratory. Unlike the steady, often complex feeding from gas clouds, a tidal disruption event is a clean, single injection of a known type of material, a star, into the black hole's gravitational jaws. It lets us watch the entire life cycle of an accretion disk, from its violent birth in a stellar catastrophe to its gradual dimming as the last bits of debris spiral in. It is a real-time experiment in extreme gravity and plasma physics, offering a front-row seat to the universe's most dramatic way of setting the table for a black hole's feast. The violence of a tidal disruption event is a spectacular exception, but the steady glow of most accretion disks requires a constant, efficient engine. For decades, a fundamental puzzle lingered. The simple friction of gas molecules rubbing together, the viscosity we compared to thick honey, is far too weak to explain the observed brilliance of these cosmic rings. If that were the only force at work, matter would spiral inward at a glacial pace, and the disks would be dim, quiet halos. Their ferocious luminosity demanded a far more powerful source of internal turbulence, a supercharged mixer churning the disk and driving material inward at the rates we see. The answer lies not in the gas itself, but in an invisible force woven through it, a phenomenon called magnetohydrodynamics. This mouthful of a term simply describes how magnetic fields and electrically conducting fluids, like the searing plasma in an accretion disk, interact and influence each other's behavior. Here, magnetism is not a passive bystander, it is the prime architect of the chaos. The key to unlocking this turbulence is a process with its own formidable name, the magnetorotational instability. Imagine the accretion disk as a series of nested rings, like grooves on a vinyl record. each orbiting at a speed dictated by its distance from the black hole. In a simple gas disk, these rings would orbit peacefully, with inner rings moving faster than outer ones, but thread a weak magnetic field through this plasma, connecting these different rings like invisible elastic bands, and everything changes. The faster-moving inner ring tries to drag the slower outer ring forward, stretching the magnetic field line. This stretching acts like a taut rubber band, transferring angular momentum, the property of spin, from the inner ring to the outer one. With its spin reduced, the inner ring loses orbital energy and drops to a tighter, lower orbit. The outer ring, gaining that extra spin, gets a boost and moves slightly outward. Crucially, this process is self-reinforcing and unstable. It creates a runaway effect where small differences in speed are amplified, generating the intense, sustained turbulence that theorists had sought. The entire disk becomes a churning, magnetic maelstrom, with eddies and whirlpools that act as a phenomenal brake, allowing matter to shed its angular momentum efficiently and plunge inward to feed the glow. This magnetorotational instability is now considered the dominant engine for driving accretion in most types of disks, from those around newborn stars to the monsters at galactic centers. But the role of these magnetic fields does not end with stirring the disk. The same twisted, wound-up field lines that drive the turbulence become the launch mechanism for the spectacular relativistic jets. Near the black hole's poles, where the disk thins and the pull of gravity is balanced by centrifugal force and radiation pressure, these magnetic fields are wound so tightly they become like colossal springs. They channel and slingshot some of the disk's plasma, accelerating it along the magnetic axis into those focused, high-speed beams that streak across intergalactic space. So the next time you see an image of a brilliant quasar or a jet spanning thousands of light years, you are not just looking at hot gas. You are witnessing the invisible hand of magnetohydrodynamics at work, a fundamental force writing its signature in fire and shaping the destiny of matter at the edge of forever. The magnetic chaos within an accretion disk defies any simple equation. Its swirling plasma, twisted fields, and warped spacetime create a system of such staggering complexity that no scientist could ever hope to solve it with a pencil and paper. To truly understand this cosmic storm, we must build our own inside a machine. This is the domain of numerical simulations, where the laws of physics become lines of code and the universe's most violent processes are tamed inside a supercomputer's memory. The challenge is to model all the forces at play simultaneously. We need Einstein's theory of general relativity to describe the black hole's gravity warping spacetime itself. We need magnetohydrodynamics to track the behavior of the searing plasma and its embedded magnetic fields. And we need to simulate how these two systems talk to each other, a discipline with a formidable name, General Relativistic Magnetohydrodynamics, or GRMHD. Writing the code for this is a monumental task, and running it demands raw computational power on an almost unimaginable scale. Scientists feed these virtual universes with initial conditions, a digital recipe of mass, spin, and magnetic field strength, and then set the simulation in motion, watching as microseconds of processor time translate to centuries of cosmic evolution. What unfolds on their screens is nothing short of breathtaking. We see the accretion disk not as a simple smooth plate, but as a turbulent ocean. Huge plasma vortices like cosmic hurricanes churn within the flow. Magnetic field lines are stretched, snapped, and reconnected in violent bursts that release enormous energy, acting as particle accelerators of cosmic proportions. Most spectacularly, these simulations show the birth of the jets themselves. From the tangled magnetic web near the black hole's poles, we can watch as coherent channels form, focusing and launching streams of plasma to relativistic speeds, exactly matching what our telescopes observe across the universe. These visualizations are more than just pretty movies, they are rigorous experiments. Researchers can tweak a single variable, like the black hole's spin, and see how the entire system responds, testing theories in a controlled digital laboratory. They reveal structures and processes like the precise mechanism of energy extraction from the black hole's spin that are impossible to observe directly. This computational frontier is where our theoretical understanding is stress-tested and refined, allowing us to decode the violent, beautiful physics written in the light of those distant fiery rings. These digital storms in supercomputers help us understand the most luminous objects ever witnessed. Quasars are the ultimate expression of an accretion disk's power, a cosmic beacon so brilliant it can drown out the light of every star in its own galaxy. The name itself is a contraction of quasi-stellar radio source because when first discovered in the 1960s, they appeared as mysterious, star-like points of light that emitted powerful radio waves. We now know a quasar is not a star at all. It is the intensely active core of a distant galaxy where a supermassive black hole is feeding at a ferocious, almost unsustainable rate. At the heart of this phenomenon is an accretion disk operating at its theoretical maximum, a state known as the Eddington limit or even surpassing it. This limit represents a delicate balance. As matter falls in and radiates light, that radiation exerts an outward pressure. At the Eddington limit, the outward push of light perfectly balances the inward crush of gravity. If the black hole tries to consume matter faster, the radiation pressure becomes so fierce it can actually blow away the surrounding gas, choking off its own food supply. A quasar is a black hole dancing right at or even beyond this extreme edge, gorging on material with a voracity that lights up the cosmos. The numbers are staggering. A typical quasar can be thousands of times brighter than our entire Milky Way galaxy, yet all that light originates from a region not much larger than our solar system. This is the accretion disk scaled to its most violent, efficient extreme. The infalling gas is so dense and hot that the conversion of mass to energy approaches its maximum possible efficiency, turning a significant fraction of the matter's rest mass into pure radiation. This makes quasars the universe's ultimate lighthouses. Their phenomenal brightness allows us to detect them from the farthest reaches of space and time. When we look at the most distant quasars, we are looking back to when the universe was less than 1 billion years old, witnessing the adolescence of the first supermassive black holes. They serve as brilliant backlights illuminating everything in their path. As their light travels billions of light years to reach us, it passes through clouds of intergalactic gas and the halos of foreground galaxies. These clouds absorb specific wavelengths, creating a forest of absorption lines in the quasar's spectrum. Astronomers decode this forest to map the large-scale structure of the cosmos, studying the distribution of matter across vast cosmic webs that would otherwise remain invisible. Beyond being mere beacons, quasars are active agents in cosmic history. Their intense ultraviolet radiation pouring out from the searing accretion disk played a crucial role during the universe's first billion years in a process called reionization. After the Big Bang, the cosmos cooled into a fog of neutral hydrogen gas. The first stars, and more powerfully, these first quasars, began to flood the universe with energetic photons. These photons stripped electrons from the neutral hydrogen atoms, reionizing the gas and making the universe transparent to light as we see it today. Furthermore, the life cycle of quasars tells the story of black hole growth. Their brilliant phase represents a relatively short, violent chapter in a galaxy's life, likely triggered by major mergers that funnel vast amounts of gas to the galactic center. By studying the population of quasars across different cosmic epochs, astronomers can trace how supermassive black holes grew from seeds in the early universe to the giants we see in nearby galaxies today. Each quasar is a flashbulb moment in this billion-year saga, a temporary but brilliant signpost marking a black hole's most glorious feast, and in its light we read the story of the cosmos itself. These brilliant quasars shine from the edge of the observable universe, but a similar, scaled-down drama plays out much closer to home. In the spiral arms of our own Milky Way, stellar mass black holes are hosting their own luminous feasts. These are the X-ray binaries, cosmic laboratories where we can watch the physics of accretion unfold in exquisite, real-time detail. The most famous of these is Cygnus X1, a system over 6,000 light-years away that was the first ever strong candidate for a black hole. The setup is a classic cosmic partnership. A stellar mass black hole, the collapsed remnant of a massive star, is locked in a tight gravitational embrace with a living, blue supergiant companion star. This proximity is the key to the spectacle. The black hole's powerful gravity relentlessly pulls stellar wind and gas from its massive partner. This stolen material, possessing too much angular momentum to fall straight in, forms a rapidly spinning, intensely hot accretion disk around the black hole itself. The temperatures here are so extreme, reaching tens of millions of degrees, that the disk does not glow in visible light. It screams in X-rays, a high-energy signature that satellites in Earth orbit can easily detect. Cygnus X1 is not a quiet, steady beacon, however. Its X-ray output flickers and flares on timescales of milliseconds, a direct echo of the turbulent chaos churning in the innermost regions of that fiery disk. Studying these nearby systems is like having a front-row seat to a controlled experiment. Because we can observe the orbital dance of the two stars, we can apply straightforward Newtonian physics to weigh the invisible object with incredible precision. By measuring the companion star's velocity and orbital period, astronomers deduced that the dark object in Cygnus X1 has a mass about 21 times that of our Sun, far too heavy to be any kind of neutron star or white dwarf. This provided some of the earliest concrete evidence that black holes are not just theoretical fantasies, but real objects in our galaxy. But the measurements go far beyond simple mass. The searing light from the accretion disk itself holds clues to the black hole's spin. As material spirals in, it eventually reaches the innermost stable circular orbit, a boundary whose size is dictated by how fast the black hole is rotating. A rapidly spinning black hole drags spacetime around with it, allowing that final stable orbit to be much closer in. By analyzing the spectrum of the X-rays, particularly the shape and width of that telltale iron spectral line warped by relativistic effects, scientists can estimate where that inner edge of the disk lies. For Cygnus X1, data suggests a black hole spinning at a breathtaking rate, close to the maximum allowed by Einstein's equations. This spin is a fossil record of the original star's angular momentum, preserved and amplified during its catastrophic collapse. Perhaps the most revealing behavior of these X-ray binaries is their ability to change state. They do not shine with a constant personality. Depending on the rate at which matter flows from the companion star into the accretion disk, the entire system can undergo dramatic metamorphoses. In a high, soft state, the accretion rate is substantial. The disk is dense, relatively cool at its outer edges but searingly hot in the center, and it dominates the X-ray emission with a thermal glow. The system appears bright and steady, but if the flow of matter from the companion star dwindles, the system can transition to a low, hard state. The disk structure seems to change profoundly. It becomes faint, hot, and geometrically thick, almost like a donut-shaped cloud of very energetic particles. In this state, the X-ray emission is dominated not by the thermal glow of the disk, but by a powerful, non-thermal corona of superheated electrons above and below it, likely powered by those tangled magnetic fields. This corona produces harder, more energetic X-rays through a process called inverse Compton scattering. Sometimes, powerful relativistic jets are launched during this hard state, linking the black hole's feeding mode directly to its ability to project energy across space. Watching a system like Cygnus X1 flip between these states is like seeing a single engine operate in different gears. Each transition offers a crucial clue. a snapshot of how the accretion disk responds to changes in its fuel supply, how magnetic fields are generated and dissipated, and how energy is partitioned between heating the disk, powering a corona, or launching jets. These stellar scale systems provide the detailed, time-resolved data that allows us to test the complex theories born from supercomputer simulations, grounding our understanding of the universe's most powerful engines in the observed flicker of X-ray light from our own galactic neighborhood. That same spin which defines a black hole's character does something even more profound to the space around it. According to Einstein's theory, a massive rotating object does not just warp spacetime, it actively drags it along like a spinning ball submerged in thick honey. For a black hole, this effect is not subtle. It carves out a bizarre region just outside the event horizon called the ergosphere, a place where the fabric of reality is pulled into a relentless whirl. Within the ergosphere, frame dragging is so powerful that nothing, not even light, can remain stationary. Every particle, every photon, is forced to move in the direction of the black hole's rotation. It is a cosmic carousel from which there is no getting off. This has a direct and dramatic impact on the chaotic material trying to form an accretion disk. As gas spirals inward from great distances, its own angular momentum might initially orient its orbit in any direction relative to the black hole's spin. But as it enters the powerful gravitational influence of the ergosphere, the relentless frame dragging begins to wrestle with the disk's internal forces. This tug-of-war between the disk's own viscosity and the black hole's spacetime twist leads to a remarkable phenomenon known as the Bardeen-Peterson effect. Imagine a wobbly, tilted spinning top gradually being forced upright by a gentle, persistent hand. Over time, the inner regions of the accretion disk are coerced or aligned with the black hole's equatorial plane. The outer parts of the disk may retain their original, misaligned orientation, creating a warped or twisted disk structure. This relativistic twisting is not a mere curiosity, it is a fundamental governor of the entire system's behavior. A stable, aligned disk is a more efficient and steady feeder. A severely warped disk where inner and outer regions fight against each other can become unstable, leading to violent fluctuations in brightness and potentially chaotic feeding patterns. This alignment process also dictates the grand architecture of the system. The powerful relativistic jets, born from magnetic fields anchored in the inner disk, are launched perpendicular to the disk's plane. Since the inner disk aligns with the black hole's equator, the jets shoot out along its rotational axis. The black hole's spin, communicated through the twisted spacetime of the ergosphere, ultimately points the universe's most powerful particle beams in a specific direction, shaping its influence across galactic scales for millions of years. The fiery ring is not just orbiting a pit, it is dancing in a whirlpool of twisted reality, and every step of that dance is choreographed by spin. The immense power of accretion disks seems to define a black hole's destiny as a cosmic glutton, forever growing in mass and influence. Yet a subtle, countervailing theory suggests even these monsters might one day fade away. This is the concept of Hawking radiation, a quantum mechanical process first proposed by Stephen Hawking. It arises from the strange behavior of empty space itself. According to quantum theory, the vacuum is not truly empty, but a seething sea of virtual particle pairs, matter and antimatter, that constantly wink into and out of existence. Normally, they annihilate each other almost instantly, but at the very precipice of an event horizon, a bizarre split can occur. One particle of the pair might fall into the black hole while its partner escapes into the universe. To an outside observer, this looks like the black hole is emitting radiation, a faint thermal glow. The energy for this process comes from the black hole's own mass, meaning it very, very slowly evaporates. The key word, however, is slowly. For a stellar mass black hole, the temperature of this Hawking radiation is minuscule, a fraction of a degree above absolute zero. The timescale for complete evaporation is astronomically long, far longer than the current age of the universe. It is a whisper against a hurricane. That hurricane is, of course, the accretion disk. While Hawking radiation represents a slow, theoretical leak, accretion is a roaring river of incoming mass and energy. For every single particle that might escape via Hawking's quantum trick, trillions upon trillions more are being captured from the surrounding disk and plunging inward. In our universe today, and for all of cosmic history so far, the process of accretion utterly dominates. The environment around black holes is not the perfect vacuum required for Hawking's delicate mechanism to be noticeable. It is flooded with gas, dust, and radiation. The black hole is not sitting in isolation, slowly evaporating. It is actively dining at a cosmic buffet, growing heavier and more powerful with each passing eon. This stark comparison puts the sheer, visceral power of accretion into breathtaking perspective. The brilliant X-rays from Cygnus X1, the galaxy-shaping jets from quasars, the violent flare of a tidal disruption event, all of these are the signatures of accretion in action. Hawking radiation, by contrast, is a faint, theoretical sigh that will only become relevant in a universe grown cold and dark, trillions upon trillions of years from now, long after the last accretion disk has faded to black. This clarifies a common misconception. When people hear that black holes can evaporate, they often picture a dramatic, fiery demise. The reality is far more quiet and immeasurably prolonged. For any black hole we can observe or ever hope to study, evaporation is not a factor in its life story. Its story is written by gravity and magnetism, by the violent inflow of matter and the spectacular outflow of energy. The fiery ring of the accretion disk is not just a feature of a black hole. It is the engine of its present reality, the source of its light and influence, and the reason we can perceive these dark giants at all. In the grand cosmic balance sheet for now and for the foreseeable future, the column marked accretion is the only one that truly matters, filling the page with entries written in fire. The brilliant glow of an accretion disk is a beacon of light, but sometimes the universe sends a deeper, more fundamental signal. In September 2015, a new era of astronomy began not with a flash in a telescope, but with a subtle wobble in a laser beam. The LIGO Observatory detected the first direct evidence of gravitational waves, ripples in the fabric of spacetime itself, caused by the final, violent merger of two black holes. This monumental discovery opened a window onto the dark side of the cosmos, allowing us to hear events that emit no light at all. Yet, when it comes to the feeding frenzy of accretion disks, gravitational waves offer a unique and complementary story. The most revealing signals may not come from the clean merger of two black holes, but from a messier, more luminous catastrophe, the collision of a black hole with a neutron star. When these two incredibly dense objects spiral together and finally merge, the outcome is cataclysmic. The neutron star, a city-sized ball of ultra-dense matter, is utterly shredded by the black hole's tidal forces in a final, violent act of spaghettification. Not all of that stellar material is immediately swallowed. A significant fraction of it can be flung outward, swirling around the newborn, more massive black hole remnant at incredible speeds. This forms a temporary, hypermassive torus of debris, a short-lived but incredibly energetic accretion disk born directly from stellar annihilation. This disk is a crucible of creation. It is phenomenally hot, dense, and magnetized, and it exists for only a brief moment, perhaps a few hundred milliseconds to several seconds. Within this maelstrom, conditions become so extreme that nuclear reactions run wild, forging heavy elements like gold, platinum, and uranium in a process known as rapid neutron capture. The radioactive decay of these newly minted elements then powers a brilliant, short-lived flash of light called a kilonova, an electromagnetic counterpart that can outshine 1,000,000 suns for a few days. This is where multi-messenger astronomy performs its symphony. The gravitational wave signal tells us the story of the in-spiral and merger, revealing the masses and spins of the original objects. The specific frequencies and evolution of the ripples can even hint at the properties of the resulting debris disk, like its mass and how quickly it is being consumed. Then, telescopes scanning the region of sky identified by LIGO and its partner observatory, Virgo, can catch the afterglow, the kilonova. The color, brightness, and duration of that light tell us about the composition of the ejected material, confirming that heavy elements were indeed forged in the aftermath. By listening to the space-time ripples and seeing the resulting fireball, we get a complete picture of a single, universe-altering event. We witness the death of a star, the growth of a black hole, the violent birth of a temporary accretion disk, and the creation of the very elements that make up our world. That faint wobble in a laser beam becomes a story about where the gold in a wedding ring ultimately came from, a direct link between the most violent forces in the cosmos and the substance of our everyday lives. The gold forged in a kilonova reminds us that these engines are cosmic foundries, converting matter into something entirely new. This conversion is staggeringly efficient, a fact that pushes our imagination toward a wild, distant future. While our most powerful reactors on Earth convert less than 1% of mass into energy through nuclear fission or fusion, the physics around a black hole operates on another level entirely. Through the combined processes of accretion and the extraction of rotational energy, theoretical models suggest up to 40% of a particle's rest mass could be transformed into usable energy before it crosses the event horizon. 40%, that is an efficiency beyond our wildest terrestrial dreams, turning a single kilogram of matter into the energy equivalent of billions of tons of TNT. This raw power immediately brings to mind the Kardashev scale, a method of classifying a civilization's technological advancement by its energy consumption. A Type II civilization harnesses all the power output of its star, perhaps by building a Dyson sphere. A Type III commands the energy of an entire galaxy. For such a civilization, a stable, feeding black hole would not be a terror to avoid but the ultimate power plant. The concept is breathtaking. Imagine a vast, engineered structure, a Dyson sphere not around a star, but encapsulating the entire accretion disk of a supermassive black hole. This megastructure would capture the torrent of X-rays, gamma rays, and light pouring from the fiery ring, converting it into usable power for purposes we can scarcely comprehend. The energy budget would be galactic. It could fuel interstellar travel on a mass scale, power computation for universe-simulating megacomputers, or even manipulate space-time itself. But the engineering challenges are so monumental they border on the magical. First, you must get there. The nearest known stellar mass black hole is over 1,500 light-years away, and a suitable supermassive black hole is millions of light-years distant. This implies a prerequisite mastery of faster-than-light travel or generational journeys spanning epochs. Then, you must build the structure itself. The material science involved is pure speculation, requiring substances that can withstand temperatures in the millions of degrees, intense radiation that would vaporize any known alloy, and gravitational tides that could shred a planet. The construction logistics around an object with an event horizon larger than our solar system are incomprehensible. Furthermore, you must control the fuel supply. A civilization would need to precisely regulate the flow of matter into the disk to maintain a steady, manageable output, avoiding violent flares or quenching the glow entirely. And finally, the ethical dimension looms large. Such a project would constitute a fundamental alteration of a galactic core, potentially disrupting the natural evolution of stars and planets for light years around. It would be the ultimate expression of cosmic dominion, with risks as profound as the rewards. While this remains firmly in the realm of speculative science fiction for us, it serves a vital purpose. It stretches our understanding of physics to its limits, asking what the fundamental laws of the universe truly permit. It transforms the accretion disk from a distant spectacle into a conceptual milestone, a benchmark for what a mature, star-faring culture might one day aspire to harness. The fiery rings feeding black holes may forever be natural wonders, but in contemplating their impossible power, we define the outer edges of our own ambition. That ultimate power plant presents a paradox far stranger than engineering. If matter is converted into pure energy, what happens to the information it contained? Every particle, every atom that spirals into the black hole carries with it a unique story, a specific arrangement of properties like mass, charge, and spin. According to the bedrock rules of quantum mechanics, this information can never be truly destroyed. It can be scrambled, hidden, or transformed, but it must, in principle, be preserved somewhere in the universe. Yet, a black hole presents a terrifying end to that story. When matter crosses the event horizon, it is gone from our observable universe, and if the black hole eventually evaporates via Hawking radiation, which is theorized to be purely thermal and random, then that information seems to vanish forever. This is the black hole information paradox, a fundamental conflict between Einstein's theory of gravity and quantum mechanics that has haunted physicists for decades. It suggests our understanding of reality is profoundly incomplete. One radical proposal to resolve this is the firewall paradox. The idea suggests that instead of a smooth, empty space at the event horizon, there might be a searing wall of high-energy particles, a literal firewall that incinerates anything falling in. This would destroy the information, but it also violates Einstein's principle that someone crossing the horizon should not notice anything special, creating another paradox. So where could the information be stored if not destroyed? This is where the chaotic, complex structure of the accretion disk might offer a clue, though a speculative one. The disk is not a simple sink. It is a turbulent, magnetic, and relativistic system that interacts intensely with the black hole's spacetime. Some theories suggest that the information of infalling matter could be imprinted onto the quantum states of the particles in the swirling plasma, or encoded in the patterns of radiation emitted from the disk itself. The scrambled history of a star could be written in the flickering X-ray patterns or the subtle polarizations of light we detect. Even more profound is the holographic principle, which proposes that all the information describing a three-dimensional volume of space can be encoded on its two-dimensional boundary, like a hologram on a flat surface. For a black hole, that boundary is the event horizon. In this view, the information of everything that falls in is not lost inside, but is smeared and stored on the surface of the horizon itself. The fiery accretion disk, then, becomes the dynamic interface where this encoding happens. Its violent physics, its magnetic fields and particle collisions, could be the mechanism that translates the three-dimensional information of infalling matter into a two-dimensional holographic record on the horizon. While these ideas remain at the cutting edge of theoretical physics, they forge a stunning connection. The brilliant, observable glow of an accretion disk is not just a byproduct of gravity. It might be part of the universe's most sophisticated data storage system. The light we analyze with our telescopes could, in principle, hold the scrambled blueprints of everything the black hole has ever consumed, a cosmic library written in fire. All that knowledge from across the cosmos arrives here not as a physical sample, but as a faint whisper of light. We can never visit an accretion disk, never send a probe into its swirling plasma. Every truth we have uncovered about these fiery rings comes from reading the subtle stories hidden within the light that manages to escape. Astronomers are cosmic detectives, piecing together a portrait of an unseen monster from the shadows it casts and the echoes it creates. The primary clues are written in the language of light itself. A light curve, a simple graph of brightness over time, tells a dynamic story. The rapid flickering in the X-rays from a binary system like Cygnus X1, with changes happening in milliseconds, reveals the turbulent churn in the disk's innermost, most violent regions. Slower, majestic rises and falls, like the year-long brightening of a tidal disruption event, map the gradual formation and consumption of an entire stellar debris disk. Each flicker and flare is a direct telegram from the edge of the abyss, encoded with information about density, temperature, and stability, but light carries more than just brightness. As we have seen, its spectrum is a treasure map. The broad, smeared spectral lines tell of whirlwind speeds. The specific warp of the iron line paints a relativistic portrait of spacetime itself, twisted near the event horizon. A newer, powerful tool in this detective kit is polarization. Light can vibrate in specific orientations, and the fierce magnetic fields within an accretion disk and its jets leave a distinct imprint on that vibration. By measuring the polarization of the light we receive, we can literally map the magnetic field structures around a black hole, tracing the invisible architecture that powers the entire engine. No single telescope tells the whole story. The true picture emerges from multi-wavelength campaigns, a coordinated assault on the mystery using eyes that see every kind of light. Radio telescopes map the vast outer structures of jets. Infrared and optical telescopes see the cooler, dusty torus and the glow of the host galaxy. Ultraviolet instruments probe the hot accretion flow. X-ray and gamma-ray observatories like Chandra or Fermi dive into the searing heart of the action, where temperatures soar to millions of degrees. It is only by stitching together these different views, from long radio waves to blistering gamma rays, that we get a complete anatomical chart of a black hole's feeding system. This is not a science locked away in ivory towers. The torrent of data from automated sky surveys is so vast that scientists openly invite the public to join the search. On online platforms like Zooniverse, anyone with curiosity and an internet connection can become a cosmic classifier. You might be presented with images of distant galaxies from the Hubble Space Telescope and asked to help categorize their shapes, identifying the spiral patterns or elliptical blurs that hint at the activity or quietude of the supermassive black hole within. Or you might scan through the light curves of stars from the Kepler or TESS missions, looking for the characteristic dips that might signal a planet's transit, or the strange, erratic flickers that could be something far more exotic. By participating, you are not just playing a game, you are helping to train machine learning algorithms and identify rare objects that professional astronomers might miss in the flood of data. You become part of the process, turning raw data into discovery. Every classified galaxy, every annotated light curve, adds one more piece to our collective understanding of how these cosmic engines and the galaxies they live in evolve. The story of accretion disks is not just told by brilliant theorists or powerful supercomputers. It is written in the light that travels across the universe, and it is being read by a global community of curious minds. The data we collect from distant quasars is more than just numbers on a screen. It is a portrait of sublime violence. That portrait has escaped the confines of scientific journals and entered our collective imagination, becoming a wellspring of modern myth and visual poetry. The swirling, fiery elegance of an accretion disk, a perfect circle of chaos, resonates with a deep, almost primal sense of beauty. It is a beauty born from contradiction, where the physics of absolute destruction creates the most luminous structures in the cosmos. This duality of creation and annihilation intertwined has made these cosmic engines a powerful muse for artists, filmmakers, and storytellers. Perhaps the most iconic translation of this science into spectacle is the black hole gargantua in Christopher Nolan's film Interstellar. The visual effects team, led by physicist Kip Thorne, did not simply invent a pretty light show. They generated their imagery by solving the actual equations of general relativity on supercomputers, rendering how light would bend and lens around a rapidly spinning black hole. The result was not the jet black void of classic sci-fi, but a luminous, warped halo, a spinning disk of gas stretched into a thin, brilliant band around the shadow of the singularity. That haunting, accurate image, dubbed the black hole's gravitational lensing ring, instantly reshaped the public's visual vocabulary for these objects. It felt real because it was rooted in real physics, and its eerie beauty made the terrifying power of a black hole feel tangible and awe-inspiring. This influence extends far beyond Hollywood. Video game designers crafting alien worlds and cosmic backdrops now regularly use accretion disk imagery to signal extreme danger and wonder. A player might navigate a ship through an asteroid field, only to crest a ridge and see a pulsating orange accretion disk lighting up a nebula, immediately understanding the colossal threat and majesty of the central unseen object. In digital art and generative design, algorithms are often fed the mathematical principles of turbulence and magnetohydrodynamics to create swirling, luminous forms that feel both alien and strangely familiar, directly channeling the chaotic beauty of these cosmic storms. This cultural absorption speaks to something fundamental. The accretion disk is a natural mandala, a symmetric structure born from chaos. Its luminous spiral speaks to growth and transformation, while its central darkness hints at the ultimate unknown. Artists are drawn to this symbolism, using it to explore themes of rebirth, entropy, and the fragile balance between order and chaos in our own lives. When a painter renders a swirling nebula with a dark center, or a musician composes a piece that swells from a quiet drone to a chaotic, luminous crescendo, they are tapping into the same emotional core that the astrophysicist explores with equations. The fiery ring becomes a bridge. It translates the cold, hard physics of relativistic plasmas into a universal language of light, form, and emotion. It shows us that understanding the universe does not diminish its wonder, it deepens it. By studying the precise mechanisms of an accretion disk, we do not strip away the mystery. We provide a new canvas upon which our awe can be painted, blending the rigor of science with the profound human need for beauty and meaning in the vast, starry dark. That cultural resonance reminds us of a profound truth. For all we have learned, the physics of these fiery rings remains a landscape of deep and thrilling mystery. The magnetorotational instability gave us a powerful answer for how disks churn, but is it the full story? In the intensely magnetized plasma near a black hole, other instabilities might compete or dominate, and the exact recipe for turbulence in different types of disks is still being written in supercomputer code. We see the brilliant glow halt at the innermost stable circular orbit, but what happens in the plunging region just inside that boundary, where matter makes its final, fatal dive? General relativity tells us that from the ISCO to the event horizon, matter falls almost in free fall, but this space is not empty. It must still contain hot, magnetized plasma screaming toward oblivion. Does this plunging flow radiate at all? Could it interact with the inner edge of the disk in ways we have not yet detected, leaving a subtle fingerprint on the light we receive? These questions probe the very edge of our predictive power. Then there are the jets, those impossibly precise cosmic lasers. We understand the basic slingshot mechanism of wound-up magnetic fields, but the details of launch and collimation are maddeningly elusive. How do these beams stay so perfectly focused over millions of light years, resisting the natural tendency to spread out and dissipate? The exact role of the black hole's spin in powering them versus the energy extracted from the accretion disk itself is a subject of intense debate and modeling. Each new observation of a jet structure from radio telescopes adds another piece to a puzzle we are still assembling. Perhaps the most dynamic unknowns exist in the realm of gravitational wave astronomy. When two supermassive black holes spiral together in the heart of merging galaxies, their individual accretion disks are violently disrupted. What happens then? The gas from both disks slams together, creating shocks and complex magnetic structures that could shine with a unique, transient signature. Detecting the electromagnetic flash that accompanies such a slow, cosmic merger would be a revolutionary discovery, linking the warping of spacetime directly to the behavior of matter in the most extreme conditions. These are not minor gaps in knowledge, they are grand canyons in our understanding. Each one represents a frontier where our theories are tested to their limits. This is why the study of accretion disks is far from a closed book. It is a vibrant, living field that hums with unanswered questions. It invites the curious, the stubborn, and the imaginative, the next generation of scientists who will look at the data from new telescopes and think that does not make sense yet. Their work will not just fill textbooks, it will redefine our place in a universe where fire and gravity write the rules, and we are only just beginning to learn how to read them. The same physics that forges a ring of fire around a black hole also sculpts the cradles of new worlds. Across the galaxy, swirling around infant stars, are protoplanetary disks, vast, flat clouds of gas and dust where planets are born. These are the serene, cooler cousins to the violent maelstroms we have been exploring, operating on the same fundamental principles but at a different pace and purpose. Here, the central engine is not a ravenous singularity, but a young, growing star gathering its material. The story begins within a cold, dark nebula, a stellar nursery. A local knot of gas and dust under its own gravity begins to collapse. As it shrinks, it spins faster, a consequence of conserving angular momentum, just like a figure skater pulling in her arms. This spin prevents the entire cloud from falling directly into the nascent star at the center, instead flattening it into a wide, rotating disk that can extend for hundreds of astronomical units. This is the protoplanetary disk, the raw material for an entire solar system. Within this disk, the same forces are at play. There is viscosity, the internal friction within the gas and dust. There is turbulence, likely driven by instabilities similar in nature to the magnetorotational instability, though the magnetic environment is far more complex. This turbulence and friction cause the disk material to slowly lose angular momentum, allowing it to spiral inward, feeding the growing protostar at its heart. But unlike the black hole disk, where infalling matter is vaporized into a plasma of pure energy, the temperatures here are far gentler. The inner regions might be hot enough to vaporize rock, but the outer reaches are frigid, allowing ices to exist. This thermal gradient is the cosmic zoning law for planet formation. In the cooler outer disk, tiny dust grains of silicate and ice, micron-sized specks no larger than smoke particles, begin a slow dance. They bump into each other, stick through electrostatic forces, and gradually build up into larger pebbles, then rocks, then kilometer-sized planetesimals. This process, called accretion, is a gentle, persistent gathering, a snowball effect on a cosmic scale. Gravity then takes over as these planetesimals collide and merge, sweeping up material in their paths to form planetary embryos and eventually full-fledged planets. The gas giants like Jupiter form fastest, their massive cores quickly gathering thick atmospheres of hydrogen and helium from the surrounding disk. Rocky worlds like Earth take longer, accreting from the drier, metal and silicate-rich material in the hotter inner zone. The entire disk is a dynamic, evolving construction site. You can see its echoes in the ordered architecture of our own solar system, with rocky planets close to the Sun and gas giants farther out, and in the flat plane in which all the planets orbit, a fossil record of that original spinning disk. This creates a breathtaking cosmic symmetry. The same physics of angular momentum, viscosity, and accretion governs both the most destructive and the most creative engines in the universe. One process feeds a black hole, converting matter into a blaze of radiation. The other uses that same spiral, that same slow inward drift, to patiently assemble the building blocks of worlds, moons, and perhaps life itself. The fiery ring and the dusty disk are two verses in the same poem, written by gravity across the spectrum of cosmic possibility. From the gentle birth of planets to the violent feasts of black holes, we have traced the same cosmic blueprint. The brilliant, chaotic whirlpool of an accretion disk is the universe's universal engine, the fiery interface where matter meets the ultimate force of gravity. It is a place of breathtaking transformation where the simple act of falling inward unleashes the power to outshine galaxies, forge elements, and sculpt the destiny of cosmic structures on the largest scales. To understand this ring of fire is to witness physics in its most extreme and eloquent form, a grand synthesis where gravity, magnetism, thermodynamics, and even the hints of quantum mechanics converge in a single, luminous spectacle. We have moved from seeing these disks as mere astronomical curiosities to recognizing them as fundamental characters in the story of the cosmos, the control panels for both creation and destruction. This journey does not end here. Our tools for listening to the universe are growing more sensitive by the day. The James Webb Space Telescope peers into the dusty hearts of young galaxies, watching supermassive black holes and their disks awaken in the early universe. Next-generation gravitational wave detectors will hear the ripples from ever more distant and exotic mergers, perhaps catching the unique hum of a black hole tearing into a neutron star's accretion disk. With each new observation, with every fresh line of code in a supercomputer simulation, the picture comes into sharper focus. The mysteries of magnetic turbulence, jet formation, and information's fate will gradually yield their secrets. So keep looking up and follow the science as it unfolds. The story of these fiery rings is still being written, a testament to human curiosity and the endless, violent beauty of a universe that turns even its darkest pits into beacons of light and understanding.